Hello everyone, this is part 2 of the Flappy Bird AI agent tutorial, and in this video I'm going to be creating the agent as well as the model for the agent. But before we start, I want to explain some general concept that you need in order to understand how the agent and the model works. So the first thing that I want to explain to you is how do we incentivize the model to do what we want it to do? So let's say that there are pipes here and here, and we have our bird, right? And every time that our bird is gonna pass a pipe, we are going to give it a reward. So when it passes through a pipe, we are going to give it a reward of say +5. And every time the bird dies, so if it hits the top, the ceiling, if it crashes to the ground, or if it collides with any of the pipes, we are going to give it a negative rewards. All right. The next thing that I want to explain is how do we make the agent know where it is within the game. So imagine if you were the model playing the game. How would you know where you are within the game? If we don't give it information on some of the states, then you're basically playing blind. Like you wouldn't see anything, you wouldn't hear anything, such. So we need to give it some values, basically the game state, in order for the agent to know where it is. So this there are going to be 5 things that we're going to tell the agent, and those 5 things are going to be the bird, the y position of the bird. We're going to give it the velocity, so the y velocity. We're going to give it information on how far away it is from the pipes, and we're also going to give it information on how far it is from the top pipe and how far away it is from the bottom pipe. All right, and the final thing that I want to explain to you is, sorry, let me just see right here. Oh yeah, I want to explain exploration versus exploitation. So what these two things mean is when the agent starts its training session, it's going to perform a set of random moves, which we're gonna call exploration, because what it is doing is exploring the game and seeing which set of moves generate the highest amount of reward. So yeah, and the second thing is exploitation. So what this is, once it's done exploring the game, it's going to start exploiting the reward system and using the set of moves that are, it's going to perform the set of moves that's going to generate the max among rewards. So just a quick recap, this is forming random moves, and this one is forming moves that gain max rewards. So yeah, that is the difference between exploration and exploitation. So that is it for my explanation of some general concepts. I'm going to be explaining some other things as we go along within our project, but for now, I think these 3 concepts are important before we start. So without further ado, let's start our project. Alright, so now that we covered some important topics for our project, let's now start finishing it. So the first thing that we're going to do within our game file is import the Python library numpy, and we're going to import it as np. The second thing that we're going to be doing is working on our getState function for our agent. So as I mentioned before, the agent requires the game state. So the 5 values, the bird y, bird velocity, etc. So we're going to returns an array of values for the agent in this function. So first off, let's do the bird y. And for each value, we are going to do something called normalization to the value. And basically what that is we're going to divide it by a number relative, or we're going to divide the state relative to some number. And if the state is a value within the vertical plane, we are going to divide it by the height of our window or screen. And if the state is within the horizontal plane, we're going to divide it by the screen width. And the reason why we're doing this is basically it improves the model's performance, and it does that because the value is small. That is kind of an oversimplification for what normalization and why we do it, but just for now, just think of it that way. All right, next off, we got the velocity t, and for this one, we're not going to normalize it because we don't have to. All right, and the next thing we're going to do is the distance to the top pipe. So distance to the pipe. So distance to pipes, set it to the set.pipe r 0 0 x divided by the screen. And actually we're gonna be needing this value, so let's create a variable for it. Closest pipe pair. Next off, we got the distance to the top of the distance to the bottom of the top pipe, and set it equal to the closest pipe pair. The top pipe, its y value, and subtracting it by the bird's y value. And also we want to normalize it, so quickly just do height. And also we want the distance to the top of the bottom pipe. Do the same thing here, so we're going to do the closest dot. Sorry, this should not be y, this should be the height. This should be the y. Y subtracted by the top of the, or the bottom of the bird, so bird y minus the bird's, plus the bird's height, and then we want to divide it all by the height of the screen. And then we're going to create an array of every state, so bird y, bird, and then we also want to return this state, and we're going to return it as a numpy array and set the data type of each value to float. The reason why we're using numpy arrays is because it's faster. Alright, next thing we are going to do is work on our play step. So the first thing we gotta do here is pass in an action variable. And this is how we're going to allow the agent to control its controls, or movement, sorry. So we're going to write if action equals 1, then we're going to make the bird jump. So bird velocity equals jumps. Alright. Next up, we are going to create a reward function for our agent. So basically how it's going to work is we're going to give it a reward between 0 of 1 relative to how close it is to the middle of each pipe. So whether the pipes look like this or look like this, depending on how close the middle of the bird is to the gap of the pipe, is going to get a reward from 0 to 1. So if it's right here, if the middle of the bird is right here, then it's going to get a reward of 1, and the further away it is, the closer it's going to get a reward of 0. Alright, so let's implement that now. So set the reward to 0. We also want to create initialize some values for every loop, every place that closest pipe pair of the center of the bird. We're going to set it to the y plus height, and then 2. Oh, sorry. Just divide the height by 2. Okay. Alright. And then the gap center. So the center, so this value, set it to the first closest pipe pair. The top pipe, so top pipe's height plus the self-vertical gap between pipe divided by 2. And to find the distance between the center of the gap and the center of the bird and the center of the gap, I'm going to call it distance y, and we're going to set it to the absolute value of bird center minus gap center. Alright. And now let's create our reward functions. So reward is going to equal the maximum value between 1 and 0 minus the distance y divided by the vertical gap between pipes divided by 2. Alright. Oh yeah, next up, we also want to give a bird a reward when it passes the pipe. So when it passes the pipe, we are going to give it a reward of plus 5. So let's work on that now. Or let's work on it. We already have the functionality right here. So we are also going to add 5 to the reward. Right? And then we also want to implement negative rewards. So within our for loop, within the collision part of it, we're going to hard set the reward to -5, and also return a value of reward, and we also want to return the final score. This is mainly for the agent. The final score is going to be the score. And the reason why we doing this part is because the score resets when we call this function. So we want to just temporarily set a score. Alright. And then also when it hits the ceiling, we're going to do the exact same thing. So let's just copy and paste it all here. Alright. And then also within the bottom of this function, we want to give it a reward of this. We're going to give it a reward whenever it passes every pipe, and this incentivizes agent to stay alive longer. So incentivize. Okay, actually, forget about that. All right, and then now we want to return the, right here, we want to return the reward done and score. Yeah. All right, get rid of that. Alright, and now that we're done everything within this file, let's run it to ensure that we have no bugs. So before we run it, however, we need to set done to the right return value. And since when we return values in such as this, it will return an array or tuple, I think. So we just have to get the position of whatever we set it to. So for this one, it would be 1. And then let's quickly run our program. So, oh yeah, okay. Just set it to 0 for now. And let's run it. All right, so seems to be working all right. I guess when we die, it doesn't immediately end the program, but honestly, that's fine. We can just manually do that with Control-C in the terminal. Okay, so we've finished everything within this file. Let's start to work on our model file. So first thing we're gonna do in here is import the Python library torch. This is how we're gonna able to create our neural network for our agent. We also want to import OS and also import numpy. We also want to set some variables from the torch class. So neuralnet equals torch.nn. Our opt-in and everything with and also this one within the torch and then function. We could also just write it as this functional. Okay, there you go. All right, next up we need to create a linear QNet class. So let's do that right now. QNet, and we want to inherit the module class from torch.nn. We want to create a constructor, and within this constructor we will be passing 3 variables, and those variables will be input size, hidden size, and output size. And what these 3 variables are is if you generally understand how neural networks work, you'll know that they have layers. They have an input layer, they have an output layer, the first layer, the last layer, and then every layer in between, which it's only going to be 1 layer. The size that will determine how many neurons will be within that layer, and we want to manually set that whenever we create an object of this class. So alright, and then next up we want to instantiate the constructor of our inherited class. So we do this by using the super function. And we also want to create two variables here as well. So that will be self.linear1, linear input size, hidden size, and also self-linear2, which equal the same thing, but this time with the hidden size to the output size. So basically, to oversimplify what this function does, basically it'll connect the input size to the hidden size within this variable, and then for this variable it will connect the hidden size to the output size. Okay, the next thing we need to do is create a forward function. So let's do that here. X And within this function, we're going to set x to the ReLU of self.linear1x. And then after that, we want to set x equal to the linear2, pass in x, and then we want to return x. And yeah, that's it for that function. All right, and then after we finished all that, let's create two functions so that we can use already trained models in the future. So for that, we're first going to create a save function. So def save, pass in self. And for this one, we want to create a file name. So file name equals just model for now. We also want to create a name for our folder path. So model folder path equals models, the current directory of our project, and then we're going to call it models. And then after that, we want to check if the path of the folder does not exist. So if the path does not exist, model folder path, then we want to create a new folder within our project. So make directory model folder path. And then if it does exist already, then we want to create a file path. So file path equals os.path.join folder path and file name. We join the folder path, this one, with our file name, and then we're going to save it to the file. So this is how we're going to do it. Torch save, first pass in self.stateDict, and then file path. And then we also want to know if it actually saved or not, so we're just going to print something to the console. So f saved model 2, and then I guess we can just do file. All right. And then after we created save function, we also want to create a load function so that we can actually use our model. So def load, and then we want to do the same thing here. So we'll just create a file name and a folder path. And then we also want to copy this over as well. Right. And then we want to check if the path does not exist again. So we write that here. And then for this time, we just want to print path does not exist. Or rather, model does not exist. And if it does exist, then we want to load the model. So this is how we can do it. Self.load stateDict torch.load file path. And then we want to print that it actually loaded. So loaded model from file path. All right, there we go. Oh, and before we continue, I want to mention that this should not be the model folder path. It should just be the file path. Yeah, all right. Next up, we need to create another class, and this class will be called QTrainer. And we also need to create a constructor. And within this constructor, we are going to be passing 3 variables, those being model, LR, which stands for learning rate, and gamma. Okay, and then let's also create some class variables. So first off, self LR equals LR, our gamma, our model, our optimizer equals, we're going to be using the Atom optimizer, meters, LR equals self.lr, and our loss function. So criterion equals and then dot the mean squared error loss. loss function. Okay, and then after all that, we want to create a train step function. Train step function, pass in the state, action, reward, next state, and done. And before we continue on with this function, we're going to pass it for now. But before we continue on with this function, we are actually going to be starting our agent first. So let's forget about everything here and move on to our agent file. So within this file, we're going to be importing some libraries again. So let's do that right here. Import numpy. We want to import torch, import random, import pygame, and then from the collections library, we want to import deck. And then from our game file, we want to import the Flappy bird class. And then from our model file, we want to import linear QNet class as well as the QTrainer class. And then, yeah, that's all. Okay. And then, first of all, so we can tell the difference between a human playing the game and the model playing the game. We are just gonna change the title of our window. So I'm gonna use pygame.display.setCaption, and then gonna do just on that Flappy bird AI training. Okay. And then next up, let's create some constant variables. So first one, max memory, set it to 100,000. Yeah, okay. Next up, batch size, 128. The learning rate, set it to 0.001. Max games, set it to 1,000. And then a max score, set it to 1,000. And just a quick recap of what all these variables are. The max memory is going to be how much memory is going to be within depending on your computer maybe, and just generally works for you, you can maybe change up all of these numbers as you want, but these numbers work well, good enough for me, so it's probably fine to leave it as is for yours as well, right? Next up, let's create an agent class agent, self, and then also pass in, no, we don't need to do that. Let's create some class variables, self.endGames, set it to 0, epsilon max, set it to 80, self.epsilon min, set it to 1, self.epsilon equals self.epsilon max at the start. Self.gamma equals 0.9, self.memory equals dec, and then the max length for this double-ended queue will be our max memory constant. And then we also want to create a keep exploring variable and then just set it to false. So just a quick recap, the number of games, so n games is going to be the number of games, or the number of times it died rather, within a training loop, or how many, depending on how long you're training it for, it will tell you how many games it played. The epsilon, it will be the exploration rate. So depending on the max and the min, which the epsilon will decrease as the more games it plays, it will keep exploring until the epsilon reaches the minimum epsilon, and then it will stop exploring. The gamma is going to be the discount factor, and basically what it is that it will determine how much to prioritize future rewards versus short-term rewards. Maybe I should call it long-term versus short-term rewards. So if it's high, it will prioritize long-term rewards more, and if it's low, it will prioritize short-term rewards more. That's kind of a generalization, an oversimplification for what it does, but just think of it like that. And then everything else you don't need to worry about. Okay. Next off, let's also create a model. Let's create a model as well. Set it to linear q net, and then set the input size. So we need to pass in these variables here. And for this project, the input size is going to be 5. The hidden size, you can do either hidden size could be from what I tested, it could be 64, 128, 256, or 512 neurons big. All these sizes work fine. Usually the one with less neurons tend to train faster, but the ones with more neurons usually tend to perform better. So depending on how good your computer is, well, you don't really need a good computer. If you have like a decent computer, it will still work fine for all of these, but depending on what you want, then you should pick the size according to that. So for now, I'll just do 64. And then for the last layer, it's going to be 2. All right. And then let's also create a trainer variable, set it to object, and set it to qtrainer, and pass in self model. The learning rate is going to equal the learning rate, and then the gamma is going to equal self.gamma. All right. Next up, we got to create all the functions for this agent class. So first off, create the getState function. And then all we got to do is just return game.getState. And if you remember, we created a getState function right here. So this function is what we will be calling whenever we run this function here. All right. Next up, we want to create a remember function, passing self, state, action, reward, next state, and done. And then within this function, we want to do self.memory.append, and then we just append a tuple of all of these values, so we can copy it here. And this will append a tuple to this deck that we created here. All right. Next up, we need to create a train function for the long-term memory. So train long memory. And then within this function, we are going to do if the length of the memory is greater than the batch size. Set mini sample memory batch size, and then otherwise we're just going to set mini sample to a list of the self memory. Okay. And then what we want to do is convert each of the states, the actions, the rewards, the next states, and every done's into its own tuple. So what that means is within this double-ended queue, there's going to be multiple tuples as we've done here within this remember function. So there's going to be multiple instances of this. So just pretend this was the deck. Hold on. Pretend this is the deck. It's going to look something like this, which each of the state being its independent from each other, right? But what we want to do is turn every state into its own tuple, every action into its own tuple, and etc. for every single one of these values. So the way we're going to do that is as such. So states, actions, rewards, next states, and done's equals zip mini sample. And then we want to convert all of these into a tensor. So self.trainer train step needs action rewards next. You know what? I could have just done this. There you go. Alright, before we move on, I want to quickly explain you what we're doing here. So first, we're checking if the length of this deck is greater than our batch size, which is we set to 128. So if this is true, then we're going to set mini sample to our self memory, and then we're going to randomize the position of every tuple within the memory. So we're going to randomize everything, switch its position as such. And then otherwise, we're just going to set mini sample to a list. So we're going to convert this double-ended queue into a list. And then after that, I already explained what we're doing here and here. So yeah. Next up, let's create a train short memory function. So the train short memory. And then we're going to pass in everything within here. So just copy and paste all of this. And then within this function, we're just going to do self.trainer.train step, and then copy everything into here. Okay. And then after that, we need to create a get action function for our agents. So in this function, we will determine when the agent should jump or when the agent should just do nothing. So do that right now. And then we need to set epsilon to some kind of equation that I've created. E raised to negative 0.01 times self.n. So if you want a little visualization of this function on a graph, this is what it looks like right here. So the x value is the number of games, the y value is epsilon, and as you can see, when the first 300 games, or I guess, yeah, first 300 games, epsilon will be a big number, and then as games go along, it'll slowly approach 0 until about, it'll slowly reach 1 or 0? Yeah, 1. Okay. Alright. And you'll see why that is important when we create this if else statement. So if the random dot round int between 0 and 200 is left hand self epsilon and keep self dot keep exploring equals true. You don't need to write that, but this is what we're doing here is saying if it's less than 0 to 200 and it is keep exploring is true, then we need to set the move to a random number between 0 and 1. So yeah, okay, and then otherwise else, then we will say state 0 equals torch dot prediction state 0 and then move equals torch prediction, and then we want to return the move after that. Okay, so as you can see, when we start off with the training, it'll be the move set will be very random because epsilon will be at around 80 to 300. Oh, sorry, yeah, 80 to 5. And then as epsilon keeps decreasing, the moves will be less and less random because since the random integer will be from 0 to 200, and as epsilon decays to a lower value, then it will be more likely that it will be less than this, so it will set a move that the neural net it will not perform a random move. There you go. Okay. All right, and then finally we need to create our train loop. So let's do that. Def train loop, and then pass in agents and game, and then we need to load our model. Agents of agent model. This should be outside, right? Yeah. Okay. Agent agent model dot load. Okay. Need to load our model from our folder. And then we need to set record 0, and then we also want to set agent.keep and then we want to say all agent.end games is less than max games. And then the first thing we want to do is get old game state, and we just say state old equals agent dot get state game, and then after that we say we need to get our move, so action get action old, and then we need to perform move. We need the agent to actually perform a move, so reward done score equals game dot play step action, and then we need to get the new game state, so state new agent dot get state game, and then after all of that we want our agent to get short term memory, or sorry, just short memory. So agent dot train short memory, state old, action, old, state new, done. And then we also want the agent remember, call the agent remember function. State old, action, state new, done. Okay. And then once we do all that, and then we want to check if done. So if the agent, or sorry, if the game has reset or it died or whatever, then we call game.reset game. Wait, hold on. Okay, we don't need to call that. Okay, agent.endGames plus equal 1, agent.train long memory. And then if our score exceeds the record score, then we set the record equal to score. And then say agent.model.save. And then we want to print games played agent.end games new line score new line, and then the record. Okay. Alright, and then after all of that, down here we just say if name equals thunder main. Then we initialize our agent game is Flappy Bird, and then we want to run our train loop. So train loop agent game, and then we want to print. And then once our train loop is done, we want to print finished training session. Okay, and then yeah, that's it for that. All right. Now let's finally finish off our model file. So, so within our train step, first thing we need to do is convert all our inputs, all of these inputs into PyTorch tensors. So if you don't know what a tensor is, basically it's a multi-dimensional array, multi-dimensional value or array. So state torch tensor np state. Well, wait, hold on. Okay. State data type equals torch.float. And then since we're going to do this for every value, let's just copy and paste it 5 times. And then say action, word, next state, and then done. Okay. And then we also want to check if the length of our state.shape is equal to 1. So that means that if this, when we converted the state, where is it? When we converted this state tuple, when we put it in its own tuple, and then if the length of this state tuple is just 1, so then what we want to do is say the state equals torch.unsqueeze state 0, and then we got to do this for all the states, so or all of these values right here. So and then next state, yep, action forward, and then done. And then this one we can just done like that. And the reason why we do this is because if the length of this state or all of these tuples is just 1, so it has 1 value within it, then for some reason PyTorch won't allow that, because PyTorch models expect a shape of at least 2 dimensions, and if it's just 1, then it won't work. So what we're gonna do is we're going to include a batch size as the additional dimension. We're gonna increase the dimension length of this value to 2, and then set it to the batch size. Set it to a batch size of 1. Okay, if that's confusing, just you can look up the documentation yourself. But yeah, that's kind of my explanation for that. Okay, and then next up, we need to make a prediction. So we need to set a prediction variable. So prediction equals self.model state. And then we need a target prediction. So what we want so we have a prediction for the model, and then we want a target for the prediction. So what we want the prediction to be. So target equals detach and from. Okay. So and then with torch.noGradient for I in range the length of done, our Q new equals reward I. If not done I, then we're gonna set Q new to the reward I plus self gamma times torch max self.model next state I. And this equation right here is what's referred to as the Bellman's equation. And basically it calculates the immediate reward plus the discounted Q value of the next state, or the next action, I think. Yeah, or the next state. Yeah, from the next state. So if you want to look up that, go ahead. But yeah, we're just gonna continue on. And then we need to set the target to a item equals Q new. Okay, and after all that, we need to backpropagate our entire model after we finish this train step. So let's do that right now. Optimizer okay, all right, and that should be everything for this project. Let's go ahead and run it and see if it works. So desktop code. Hold on. Okay, python agent.py. Okay. has no attribute self dot velocity. Okay, up here, I'll make sure that action is returned as a non-float, or turns into a long non-float. Okay, and there you go. Yeah, that should be it for this AI tutorial. You'll see it is just jumping up just randomly right now. It's not really trying to go for the center, but as you play more and more games, it should get better as you train it longer and longer. So yeah, that is it for this tutorial. If you liked it, please subscribe and like this video, and thank you for watching. Goodbye.